name is Mike Miga, and I'm a professor of biomedical engineering here at Vanderbilt University. I'm also the director of the Master of Engineering in Surgery and Intervention program. And for those that may not know about that program, this is a professional Master of Engineering program, and it's designed to provide advanced technical skills in the areas of cutting-edge areas of surgery and interventional technologies. It's also meant to provide aspects of professional development as well as soft skills. We also have a capstone design experience where the students actually build their own prototypes as part of the program. And then our hallmark feature is the amount of clinical immersion experiences that the students have as well to really understand the domain where things work. So if you're interested, be sure to look up Vanderbilt's Master of Engineering in Surgery and Intervention program. The website's right there if you're curious. And with that background done, I'm going to go into a little bit about what today's discussion is. And so in previous panel discussions, we've discussed the roles of engineering in surgery and intervention with respect to problems in the open software area, robotics, careers in industry, entrepreneurial endeavors, digital twins, and other new generational devices. In today's panel, we're going to be tackling a new topic. We're going to be looking at designing for the low resource environments as we explore kind of cutting edge interventional technologies for challenges in global health. This is a whole new area. To chat about these things, I'm excited to introduce two of our panelists today to kind of sit and chat, and we'll shoot the breeze about it. So first up, let me introduce Dr. Audrey Bowden, who is a Dorothy J. Wingfield Phillips Chancellor Faculty Fellow and Associate Professor of Biomedical Engineering at Vanderbilt. And she'll be providing some insights on topics in this area associated with her experience in her field in the areas of biomedical optics, microfluidics, as well as potentially point-of-care diagnostics. Our second panelist is Dr. Nabil Simaan. He's an IEEE and ASME Fellow. He's a professor of mechanical engineering and computer science and otolaryngology here at Vanderbilt, and will be providing us insights on this topic with respect to kind of advanced robotics as well as surgical guidance. So also in full disclosure, I am a co-PI of the grant from the Wellcome Trust. Dr. Nabil Simaan is the PI on and project director, so I kind of work for him these days a little bit, but just to put that out there as a full disclosure. So welcome everybody, and I welcome to you both. I appreciate you both taking the time out to kind of shoot the breeze with us on this topic. I know it's near and dear to your hearts, and so it's nice for you to kind of come on. I know you're busy people. So I'm going to jump right in with the first question, and really it's more of an introductory aspect to the audience, which is it's a little more basic. So part of the purpose of this is to kind of introduce your fields of study to potential our audience members, as well as potential trainees out there that might be interested in your area. As I said, I'm a director of this ESI program, and so it kind of gives a sense of who the faculty are that are part of it. So I'll start with you, Audrey. Perhaps you can tell us a little bit about your background area or fields of study, and perhaps maybe what drew you to it, and then we'll go on to you, Nabil, and ask the same question.
Sure. Thank you, Mike. I'm really excited to be here and to interact with this virtual audience. So my area of research is in the area of biophotonics or biomedical optics. And essentially what we do in my lab is we harness the power of light to assess health, detect disease, and monitor treatment. And that looks like a lot of different things, but mostly what we do are develop diagnostic platforms and imaging platforms and sensing platforms that use light as the sensing medium to understand what's happening in the body so that we can help people get better. So all the problems that I work on are somehow connected to medicine or biology. Most passionately, I'm interested in medical problems. And so in terms of what drew me in, I've always wanted to work on something that's going to improve health. When I was in high school, I thought about becoming a medical doctor, and then I realized that there were other ways to impact healthcare outside of becoming a medical doctor, and engineering was something that I was drawn to as well. And so biomedical engineering in general, I think, is a really wonderful intersection of those two interests to build and solve problems and help people, and then the biomedical side to kind of do that in the domain of healthcare. So that's how I got into this. And then my background is as an electrical engineer as an undergraduate. And so within that domain is where I really started to learn about optics and light. And I thought it was just a really neat feature. I mean, light is just so central to life and how we interact with the world. And it was really in the process of writing my essays for graduate school and trying to figure out what I wanted to do with my life after college that I even learned about the field of biomedical optics. And so once I learned about it, because I'd already been interested in optics, and then it just kind of really drew me in with its opportunities to affect healthcare, I just kind of found my area. So.
That's great. That's great to hear. Switching gears a little bit with Nabil, because he's a mechanical engineer, which I'm always amazed. BME in general, biomedical engineering, small b biomedical, covers all these different engineering disciplines. So Nabil, maybe you can tell us a little bit about your areas of study in mechanical engineering and kind of what drew you to it too.
Yeah, again, thank you for having me participate. I guess I am like I said, a mechanical engineer. Typical mechanical engineers make machines for a variety of reasons. What drew me into it was I started as a roboticist, and I asked myself, like, what is the most challenging area that offers me the most amount of really interesting research problems with a societal benefit, like very clear societal benefit. And surgical robotics, which is kind of my area, happens to be one of those areas where if you solve a problem in surgical robotics, you will immediately also have additional impact in general on robotics, because surgical robotics requires you to deal with a lot of constraints. You're dealing with shifting environment, soft environment. These are hard problems in terms of research in robotics. And it also offers a huge amount of opportunities for exploring design creativity. The fact that we as a society have asked surgeons to switch from open surgery to minimally invasive surgery to make things better for the patients, that's basically asking them to do the procedures with their hands somewhat tied behind their back. So often a lot of what we do is try to relieve some of those constraints from the surgeons while still retaining the benefit to the patient. So really, when I think about how my career evolved, it has always been the interest in the exploring the creative side of things, the design aspect, and then the intriguing research questions that come as a byproduct of being in the area of surgical robotics. Yeah.
That's great. And we just had a lab meeting this morning with you, and I know looking across the scope of the work that you're doing on your projects, it's just incredible how it dips into all the different disciplines. I think, it just goes to show kind of how you move through different domains, in order to kind of accomplish this for robotics. So the next question, staying with the same order, Audrey first, we introduced the topic of this, little discussion of problems in global health, or challenges in global health, and the idea of low resource environments and design within low resource environments. I think a lot of our audience, we understand those kind of areas a little bit, but I think a lot of our audience probably doesn't, as well as the students and potential trainees that are out there probably don't understand what that means exactly. So I guess, can you help folks understand what does it mean to kind of work in this area, and what does this domain actually mean terminology-wise to you? Audrey, starting with you.
Yeah, I think that's a great question. And so when I was kind of coming up in my career, I'd heard about technologies for low resource settings, and I was really drawn to that because oftentimes low resource settings were associated specifically with kind of poor or area just really didn't have financial resources to have kind of first world healthcare, for example. And so I was interested in that because I was wanting to help people. But actually, as I started to work in this area on my own, I started to take a broader view of what that means. And so I no longer personally use the term low resource. I typically go for what I call resource constrained. And that's opened the problem up a bit for me because I think that poverty and cost is not the only constraint that we need to think about when we're designing these technologies. And actually, when you broaden it, you realize that there are so many other interesting areas that offer potential challenges and problem opportunities for this type of work. And like Nabil said, you solve one problem in one of these domains and it translates very easily into some of these other domains. So when I moved to Vanderbilt, I started teaching a class called Optics for Resource Constrained Settings. And I developed this concept of the constraint matrix. And so every week or 2 weeks, we kind of talk about different environments, so different environments, and think about the different types of resources that can be constrained. And so moving beyond cost, I think we can think about things like infrastructure or knowledge of the healthcare provider or knowledge of the patients, the form factor, the portability. And so because of that, I really think that working in this space means thinking about developing technologies that are applicable for all sorts of contexts, not just low and middle income countries, but places like rural Tennessee, right in our own backyard, places like how do we do at-home healthcare, which became really important, really popular in the wake of the COVID pandemic, or emergency medicine, or even the surgical suite, which is a topic probably that's near and dear to this audience. That offers some constraints. They're not all cost-based, right? But anyone who's been in a surgical environment realizes there's just not a lot of space there, right? And you have to think about how do you redesign your technologies so that they can be used effectively in that environment. We also talk about in that class, we cover like space health. We talk about, how do you do surgery on the battlefield? So just these other environments where there are constraints and there are resources that are limited, but they're not, I wouldn't necessarily call them, low resource in the poverty perspective.
Gotcha. No, that's a great, good comprehensive definition. I think that's awesome, and I think it's something that we don't think about as much, but I mean, it really does influence the way you do design. I think that's really true. We're going to get into that in a little bit in a second. But Nabil, do you have anything to add to that? I mean, you're working in the area of surgical products and things like that. What's your kind of interpretation, your thoughts about it?
I would say everything that Audrey said resonates with me. I'd like to add to it. Just often you have to also consider the logistics. So, for example, in certain countries, there are some logistical challenges that make things really, really hard. So, for example, here in the US and in Europe also, we kind of assume that CO2 is available, right? And and you can use it for insufflation during surgery, but apparently it is not something that's it's a strong assumption in certain parts of the world that just because you have CO2, that means you also have the logistics to deliver it and have it ready. That is certainly not the case. Even when you're designing a system, considering the power requirements, our grid tolerates much higher power specs on regular circuit breakers, whereas other countries, they have potentially lower specs and also a higher likelihood of interruptions. So you also need to think about that. And just another example of lower research setting may not necessarily be have to do anything with not having money. So workers that are on an oil rig out somewhere in the middle of the ocean, they don't have access to a full hospital, but there may be some kind of technological solution for an emergency intervention that could be life-saving in that setting. And because of the nature of the constraints you have, that is also a lower resource setting, and same for battlefield interventions. And when I think about the things that we have to consider, for me, I always start with what is the minimum task specification or design specification that I need to meet without all of the bells and whistles, because it kind of remains focused on achieving the goal from a perspective of the patient and keeping both the cost and the ease of deployment. So just because you design something that works doesn't mean that people will want to use it. It also needs to be very easily deployable, and just like Audrey said, essentially integrate seamlessly in the workflow. So it's not something that will make people shift the way they do things or even have to reconfigure their OR. Thank you.
Those are great explanations. I really thank you for that, both of you. That's a real great description to help our audience kind of understand what this area is. And actually, it's almost like it's really a new area of design where you really have to take into account all the environmental variables, and they can be quite diverse when you think about what those are. So I'm going to stick with Nabil this time for the next question, which is, clearly these have engineering design constraints that are unique, and you've kind of both emphasized that in a couple of different examples. And you're kind of moving into your own areas a little bit here. So do you have any examples from your own work and that you're really involved with right now that maybe you could share with the audience just to kind of give some sense of a nice concrete example of kind of your experience in the area? And I'll go to you next, Audrey, with that same question.
Yeah, thank you. So I guess one of the current projects we are working on, the one that you mentioned, is essentially trying to address shortage of access to clinical care providers, specifically surgeons. There are certain countries where you don't have enough massive or numbers of surgeons that can be freed up to train the next generation of surgeons and certify them in terms of skill. So one of the areas that I'm working on is how can we use robotics and in some aspect with your help and with the help of the rest of the team members, how can we use machine learning and finite element modeling of tissues to create a holistic training environment that can train essentially young surgeons how to practice doing surgery, and also we can present them with a variety of anatomical variations and variety of tricky situations that they would not simply have the opportunity to encounter in that physical setting that they have because of the lack of access to mentors, also because of the low numbers of surgeons available to work with. Just to give you an example, one of the countries we're working with is Kenya, and they have somewhere less than 400 board-certified surgeons for the entire population. So it's very difficult to justify freeing up one of these people to run a training program when their hands are so busy trying to save lives. So that's where we think technology can be really helpful in terms of accelerating skill, and that some of that same technology can also be used and adopted in non-resource limited settings, such as in the US, right? Because there is a financial benefit to also freeing up a high-paid surgeon to be able to offer a higher clinical volume. Thank you.
Yeah, that's really amazing. When you think about that, the idea of we make assumptions that we have instructors and we can have trainees, and this is an area where you're resource poor for instructors because they have other things to do given the constraints of the environment. I think that's really interesting, just a different way. Audrey, I guess you're in a different area altogether, different field altogether. What's been you have any example of a way of that you looked at this problem in your work?
Yeah, sure. So one of the ways that we've looked at this problem in my work has to do with a technology that I've been working on since I was a graduate student. It's called optical coherence tomography, or OCT, and it's basically an imaging method that uses light to see inside of the body. And traditionally, these OCT systems, which are used as the gold standard for many ophthalmic diagnostic experiences, these machines are big and bulky, and they sit in specialists' offices. But a lot of people don't have vision insurance, and so they can't always go to the specialist. They see their primary care doctor, and or they have diseases with comorbidities that are going to cause them to have problems with their eyes, and they're seen first by their endocrinologist or their primary care doctor. So we've been thinking about how do we design technologies that can be used in the primary care suite. And so firstly, there's a constraint there around cost, because oftentimes these locations, these clinics don't have the money to invest in a really large and costly machine. But then there are other things like form factor and storage, right? Where are they going to keep this big machine? They don't have that room. You go into a doctor's office and they want to have all the equipment that they need to diagnose you there if you're visiting your primary care physician. So in thinking about those kinds of constraints, we've been really challenged to think about new ways of engineering and designing OCT systems, for example, that would allow us to reduce the form factor significantly, reduce the cost significantly. So one example of that is one of the key components in OCT is often a grating, and a grating is an optical component that when you send white light into it, for example, will split the light into its different colors. And that's an important and critical step in the OCT processing pipeline, but it takes up a lot of space, not to mention it takes up a lot of cost. So one of the things we've been exploring in our lab is how can we use something that has a totally different way of operating. And we've been looking particularly into the use of things like Scotch tape. We can just take a piece of Scotch tape and use that instead of a grating, and we get a very different spectral distribution profile. But when we couple that with machine learning and couple that with other computational tools, we can back out the same kind of information, but we can do it with a much cheaper and much more compact component that will allow us to, to make those critical design changes that are needed in order to make this a plausible technology in that environment.
Oh, that's great. That's very clever. Yeah, that's. I mean, this is just again another example of kind of a whole different approach, looking at different problems and still, running into these constraints and coming up with really adaptive solutions to kind of for the environment. So I guess you kind of took a couple of my questions away, but I'm gonna ask another one that's a little bit more. Thinking a little bit more futuristically. I mean, you've given us kind of concrete examples right now, and we're in a situation where things are changing, environments are changing. We're looking at certainly wealth gaps that are happening in different parts of the world. I guess when you look ahead at different aspects of healthcare, from a futuristic kind of standpoint, what are the things that are on the horizon really that you think are really going to influence kind of where engineering is going to happen? Do you have any sense of what you think on the horizon? Maybe I'll start with you, Audrey. Do you have any idea what you would probably kind of think about for any trainees or folks that are looking at the field? What's on the horizon for this kind of area?
Yeah, that's a big question, and I certainly don't have all the answers. And I wish I did, but I mean, definitely, I think we're seeing a huge revolution in what is possible with AI. And so I think that's really just going to feature into a lot of, the new transformational solutions, anything from, training, like Nabil mentioned, to making better, simpler, more compact devices, like I mentioned. So I really see kind of understanding AI and the power of it and how to use it properly, though, right? So there are a lot of challenges that come with AI. Particularly, there are challenges, for example, around bias. And as we think around this topic of global health, right, one of the things that comes to mind for me is, when we're designing biomedical technologies, how sure are we that they're going to work for everybody? How sure are we how sure are we that they're going to work for the globe, right? Not just for the one population that you tested for. And so that means we need technologies that are going to allow us to, one, be accurate across all different types of individuals with all different types of backgrounds, identities, compositions, etc. We also need, methods to be able to bring people into, testing environments and clinical trials and clinical studies so that we can get the appropriate testing done and validate the technology. But with all these things, I definitely think AI plays a big role, or will play a big role in that. So that's one area.
That's a great example, I think. And also, I think, you don't think of, social media being everywhere, but it does have, that kind of technology is propagating quite wide and broad. So the idea that these things are going to be things that we have to address, I think, and especially with the amount of data that's coming through, a century ago, we would never get that kind of data from around the globe, but you can get that, not equally sampled, but you can definitely start to hit on some of these problems, and how we interpret that's going to be a big thing. Nabil, do you have anything to add to that?
Yeah, so I mean, I'm excited about, when I look at surgery, right? I would say, next generation systems, I hope would use as much sensory information as possible to essentially have the robot and computer form a concurrent model update of the environment, the surgical scene, and form a situational awareness of the holistic procedure, so that it's kind of computer aided management of the entire surgical process from perioperative care all the way through surgery and after. And that's where use of technology and figuring out how to integrate into the infrastructure of hospitals to be able to ensure this both use of technology to help with every possible point of failure of patient care. That's where I think we will have potentially big gains in patient benefit. Other areas, relate to semi-automating some of these procedures that are tedious to surgeons and could potentially be done better with the correct type of intelligent robots that have the right amount of sensing to be able to help. But when I look at the global setting, I would say going away from the paradigm of a very, very large robotic system that takes over several $1 million to buy and use, to more kind of low-cost, intelligent handheld devices, or even devices that work cooperatively with surgeons that are several orders of magnitude lower, and possibly also using technology to convert what currently is an office-based procedure to an OR, a surgical procedure that requires an operating room, into an office-based procedure that drastically also reduces the cost of care, and that's where sometimes technology can help you achieve that.
Yeah, that's great. I mean, actually, when you combine all these answers, I think, you're looking at AI, you're looking at data transmission, you're looking at automation, you're looking at low-cost automation, and you're thinking about, our ability to transmit information as well as receive information. I think there's certainly opportunities to, build conduits of expertise outside of the immediate kind of high-tech hospitals. I know you've done some of this as well, Nabil, dealing with teleoperation and whatnot. So I think there certainly is a lot of opportunity out there. I think it remains to be seen what that's going to look like exactly, but I think you've both hit on some really great areas for our potential trainees as well as the audience to think about in the future. Another question, so getting a little bit near the end here. So I guess, you're both expertise, you have both, deep expertise in your given areas, and our Master of Engineering in Surgery and Intervention program concentrates on a lot of the things you touched on, things like medical devices, robotics, instrumentation, therapeutics, modeling and simulation, AI, guidance and delivery, and imaging, these kinds of things. I guess when you think about the nature of this area, do you have any advice on training, for potential folks that are looking to get into this, or even some of the maybe potential trainee in our program? What are the kinds of skill sets that you think that the students should think about and are really important? Clearly AI might be one of them, but do you have any guidance for folks that are kind of looking to get into it? Sorry, Nabil, I'll go with you first.
Yes, I mean, I deal more on the side of kind of system design. So I would say, we have several courses offered here at Vanderbilt. On my side, I offer a couple of classes. One is in the robotics and control class. The other one is a slightly more advanced class that goes much deeper in terms of modeling of new robot architectures, including often what students do is our research projects directly tailored at medical applications. I also sometimes offer a kind of design of medical devices from a perspective of a mechanical engineer. So how do you design essentially mechanisms that do a specific task for surgical applications, graspers and other surgical instruments. I would suggest that students also take advantage of the fact that we do have a lot of flexibility in our program, so they can also choose classes from CS that might build their programming background, which certainly is a requirement nowadays for a undergrad and also a master's graduate. Thank you.
Great. Audrey, you have to add for that?
Yeah, sure. I guess I would say, I mean, I think in terms of coursework, if people are coming for masters, obviously they want to go deep so that they can get that mastery. I mean, that's the main purpose of the degree. But I also want to encourage people to think about keeping a little bit of breadth. And I'll give an example. I feel like in my research in particular, but I've seen this in others, students who, for example, are interested in the software side of things, they want to program, they want to, do image processing. The best students in my lab who've done that work have the skill set in image processing, but they also understand the physical hardware and they understand the biology of the problem, because that allows them to better tailor their algorithms and to better understand what is the signals that they're seeing and how they can extract more meaning from that. And so I want to encourage people to not just pick one side or the other. I really think, there's value in bringing both of those things together. And in a lot of, the proposals that I'm reviewing and other things that I've seen, the new interesting forefront of a lot of AI research even is using this physics informed or biology informed aspect, right? You can't just focus on the model. You need to understand the problem.
Mm-hmm.
And so I think as you think about your coursework, especially as you have this opportunity to also go deeper with the design, don't just focus on, the one narrow piece of it that you think you came here for. Try to understand a more holistic picture, because overall that's actually going to end up making you a better engineer.
That is a great point. In fact, in terms of the master's program that we have in engineering and surgery and intervention, the whole point of it was to allow students to really look across the disciplines. So we allow students to take courses in mechanical and biomedical and electrical and computer science, largely because we recognize even among the faculty, we need to bring in different skill sets in order to kind of realize, truly realize the designs that we're looking at really in terms of this area as well as other areas within surgery and intervention. So that's about all the time we have for today, folks. And I'd like to thank Dr. Bowden and Dr. Simaan for coming on the air and taking the time to really inform us about this kind of novel development in global health challenges. And so it's really something I really appreciate them. I know exactly how busy they are, so it means a lot to me, and I'm sure the audience really appreciates it. So as far as last notes, this is our final installment for this academic year. So if you did not catch, we have 5 other sessions that are also of different topics. So feel free to look back in our archive to kind of see some of the other things that we talk about. And I always give my last disclaimer is I'm no professional podcaster by any or webcaster by any stretch of the imagination. I'm just an engineering researcher. So if I've fumbled and bumbled my way through this, as I always tell my kids, I'll do better next time. So take care, folks, and I hope to see you next time. Thank you.